Hi, I'm Rachel de Silvio, and I'm going to talk to you today about the electrical pacemaker activity of cardiac autorhythmic cells. Autorhythmicity is a term that describes that the action potentials that the heart generates are by itself, without nerve stimulation, causing the heart to contract rhythmically. There are two types of cells in the heart. The autorhythmic cells do not contract, but rather start and conduct the action potential that contracts the contractile cells of the heart. These cells are also unique because they do not have a resting potential. These cells are present in the sinoatrial SA node, the atrioventricular AV node, the bundle of His, which is the atrioventricular bundle, and the Purkinje fibers. The second type of cell in the heart are the contractile cells that make up 99% of cardiac muscle cells. They do the mechanical work of the pumping of the heart. They do not initiate action potentials like autorhythmic cells do. The sinoatrial SA node is located in the upper wall of the right atrium of the heart. It initiates the action potential that causes the heart muscles, the contractile muscle cells, to contract. A normal electrical impulse will move from the SA node to the two atria, causing contractions. The electrical impulse then spreads to the atrioventricular AV node. The AV node is located in the wall of the heart between the right atrium and the right ventricle. The AV node amplifies the signal it receives and sends it to the ventricles, causing them to contract. The pacemaker potential is when the autorhythmic cell membrane slowly drifts to threshold. Instead of having a resting potential like nerve and skeletal muscle cells, autorhythmic cell membrane potential slowly depolarizes between action potentials until threshold is reached, creating an action potential. This cycle of action potentials continue to occur, drift, fire, repeat, and spread throughout the heart, stimulating beating at steady intervals without the need for the nervous system. There are three changes in ion movement that give rise to the pacemaker potential. The first one is an increase inward sodium current. This causes slow depolarization to threshold. Sodium enters through voltage-gated channels unique to cardiac pacemaker cells, called funny or IF channels. Funny channels open when the potential becomes more negative, hyperpolarizes, instead of less negative like normal voltage-gated channels. This unique behavior allows for one action potential to lead directly to moving the cell membrane potential to threshold again. The second ion change is a decreased outward potassium current. Unlike nerve and skeletal muscle cells, the permeability to potassium changes. When the membrane potential reaches negative, the potassium channels slowly close, decreasing the amount of potassium that leaves. The third ionic change is the increased inward calcium. When funny channels close, T-type calcium channels open, helping to depolarize the membrane. Once threshold is reached, the calcium channels close. These ionic changes bring the membrane to threshold. Once threshold is reached, the L-type calcium channels are activated, and polarization, which is the rising phase of the action potential, occurs. The L-type calcium channel is a long-lasting, voltage-gated calcium channel. When this channel opens, there is a large influx of calcium. This action potential of the autorhythmic cells are different than nerve and skeletal muscle cells, because nerve and skeletal muscle cells have an influx of sodium instead of calcium. Then the calcium channels close and potassium channels are activated, causing potassium efflux accompanied with the falling phase of the action potential. An electrocardiogram, or ECG, shows the spread of electrical activity through the heart. An ECG can help diagnose abnormal heart rates and arrhythmias. The P wave is caused by depolarization of the atria. The QRS complex is caused by depolarization of the ventricles, which hides the repolarization of the atria. And the T wave is caused by repolarization of the ventricles. The current research done in 2012 on the effect of ivabradine on pacemaker activity was published in the Journal of Cardiovascular Electrophysiology. The name of the article was Effects of Ivabradine on the Pulmonary Vein Electrical Activity and Modulation of Pacemaker Currents and Calcium Homeostasis. Their hypothesis was if rabbits are exposed to ivabradine, a heart rate decreasing agent, then the rabbit's pacemaker activity and pacemaker current, IF, will decrease. The control group that they used to compare was the pacemaker activity before the administration of ivabradine. The 4 experimental groups was the pacemaker activity after ivabradine administration. The first group was 0.3 micromolar of ivabradine. The second group was 3 micromolar. The third group was 10 micromolar. And the fourth group was 30 micromolar of ivabradine. Their results were that ivabradine decreased spontaneous activity of pulmonary vein cardiomyocytes by 6% in the 0.3 group, 32% in the 3, 49% in the 10, and 85% in the concentrations of 30 micromolar. This study showed a rate-dependent effect on the ivabradine. So ivabradine decreased the pulmonary vein beating rates more in the faster pulmonary vein cardiomyocytes. For the conclusion, this study was one of the first to collect data that supported that ivabradine suppressed the spontaneous activity of the pulmonary vein cardiomyocytes and the IF channels. The application of this research would be in treating atrial fibrillation, which are irregular and rapid heartbeats.